Okay, so in the previous video we saw how to define the work done by a force, and we defined it to be just a line integral. So the work is equal to the line integral along a path C of the force in consideration dot product dr, which is the line element along the path C. And this is the kind of fundamental result that we're going to use to calculate a couple examples, find the work done by some forces. Okay, so for example, let's consider, okay, so example, whoops, what am I opening? Okay, so let's consider a general example. Example 1. So let's say that we know the force that is applied on a particle. Okay, so F is equal to, and let's say this is x squared in the direction I plus 2zj plus yzk. Okay, this is the force that is being applied on a particle, and that particle moves in a path C. This path C is, say, a circle. It's going to be x squared plus y squared equals 1. Okay, so we have a force acting in 3 dimensions, and we want to find the work done by that force when it moves a particle along a circle in the xy plane. So let's draw a small diagram of this path. So here we have our circle. There you go, and the two axes. So this is the y-axis, this is the x-axis, and you can imagine the, you can almost imagine the z-axis that is pointing up right here. Okay, and this is our circle, and we're going to consider the clockwise direction. Okay, so this is our path C. Okay, so what now? So the standard method really is just go in with the line integral. So integral along the path C of x squared I plus 2zj plus yzk dot product x squared plus y squared, and here we run into the problem. How do we define dr? Well, notice that dr dt is going to be the time integral of r, and r is just the vector, the position vector of all the points along C. Okay, so how can we write this path in terms of a vector valued function? Well, one way would be to parameterize this path. In other words, for example, C could be defined as the parameterization with x equal to cosine of a variable u, and y being the sine of a variable u. This is the parameterization of a circle of radius 1. If we use this parameterization, then we can define r to be a function xu, yu. Okay, this would be equal to xui plus yuj. Okay, where actually this should be, to be more precise, this would not be x, this would be xu, and this would be yu. Okay, so we'd get x of u and y of u. In other words, this is equal to cosine of ui plus sine of uj. So what is the derivative with respect to, well, not time at this point, because we didn't parameterize it with time, we parameterized it with respect to u, which is a random variable that we assign. Okay, so what is this equal to then? It's just going to be the derivative of the components, so negative cosine of u I plus negative sine of u I, sorry about that. Okay, so negative sine of u I plus cosine of u j. Okay, so we can plug this in here. So we get negative sine, negative sine of ui plus cosine of uj. And what are we integrating with respect to du? Alright, why? Because in the physicist way of thinking, what we could then do is just write dr equals negative sine of ui plus cosine of uj du. Okay, this is kind of the physicist way, just multiplying by du. There's a more rigorous way, but this is a physics course, so I'll just keep it at that. Okay, here we run with our second problem. Because the force is still not parameterized, I still have it in terms of the coordinates. So I'll have to rewrite the force. Okay, so how do I parameterize the force? Well, we're just going to substitute these into here. But notice, what is z of u? Z of u is just 0 because we said the circle is in the xy plane. Okay, so in here I should actually say z of u equals 0, which means that the j component and the k component disappear because they contain z. All we're going to remain with is the I component, which points in the x direction. And what is that I component? Well, it's just going to be x of u squared I. X of u squared is cosine squared of u I. Okay, so we can plug this here into our expression, and we get that the work is equal to the line integral, not the line integral anymore, because we've parameterized everything. We're integrating with respect to a variable u now. And what does that variable run from? It runs from 0 to 2 pi, right? Because if you want a full circle, then u has to go from 0 to 2 pi, okay? And that is because it's in the clockwise direction. If it had been in the anti-clockwise direction, we would have used different parameterizations. Okay, so u goes from 0 to 2 pi of cosine of u squared I dot product negative sine of u I plus cosine of uj du. Obviously this term right here, the j term, we don't really care about because it's 0, it's going to be 0 anyways in the dot product. So we end up with 0 to 2 pi of the integral negative sine of u cosine squared of u du, and this is equal to, well, it's going to be cosine cubed of u for sure, but it's going to be 1/3, right? Because when we take the derivative of this, we get, by the chain rule, 3 times 1/3, which cancels out, cosine squared of u times the derivative of cosine of u, which is negative sine of u. That's great, and it goes from 0 to 2 pi. And in the end, what do we find? This is a very important thing actually. we find that this work right here is cosine cubed of 2 pi is 1 minus 1/3 times 1. This is 0. This is very interesting because the work done by the force when it moves the particle along this path is 0. It doesn't do any work. And this is a very special property because it means that in this case we don't have to add energy to the system to make this particle move because this work is equal to 0. If we use the work energy theorem, what we would find is 1/2 m VB squared minus 1/2 m VA squared is equal to what? It's going to be the work in moving it along this path, 0. And that makes sense. This is a closed path, right? Which means that A and B coincide. Okay, this is both A and B. So expanding from the work energy theorem, we find that VB is equal to plus or minus VA. This means that the initial velocity of the particle in the closed loop is going to be its final velocity as well. Okay? So hopefully that cleared up how to calculate a line integral. We'll do many others